One of the useful thing about Moivre's theorem is it gives us another way to work out some trig identities. So let's just start off with the double angle ones, which of course we already know. We've got our cos 2 theta and sin 2 theta. But what we can do is this. By Moivre's theorem, we can say that cos theta plus I sin theta squared is the same as cos 2 theta plus I sin 2 theta. We multiply the argument by 2. If I expand the right-hand side out, I get cos squared 2i sin theta cos theta minus sin squared theta. If I then equate the real part and the imaginary part, as we said with complex equations, the real must equal the real, the imaginary must equal imaginary, we get cos 2 theta is cos squared minus sin squared. Sin 2 theta is 2 sin theta cos theta. So it's a neat way of proving those particular results using imaginary numbers. But of course we can apply that further, as long as we can always expand out the right-hand side. But let's do the 3 thetas. So we're going to find sin 3 theta, cos 3 theta, and tan 3 theta. So same idea. I'll start with Moivre's theorem. Well, cos theta plus I sin theta all cubed would be the same as cos 3 theta plus I sin 3 theta. If I expand the right-hand side, so I'll start with cos cubed. The powers of cos will go down by 1. The powers of sine will go up by 1. And the coefficients go 1, 3, 3, 1. But of course, I squared is negative 1, so I've tidied up the last two terms there. I haven't worried about I squared. I've called that negative 1. And I cubed, I've called negative I. And then we can do the same idea. Well, the real part must equal the real part. The imaginary part must equal the imaginary part. So sin 3 theta is 3 sin theta cos squared theta minus sin cubed. Well, if I want it just in terms of sine, then I can replace the cos squared with 1 minus sin squared. Tidy that up. There's the result, 3 sin theta minus 4 sin cubed. So the real parts, cos cubed theta minus 3 sin squared cos. Again, if I want to get rid of the sin squared, we'll make that 1 minus cos squared. And we get our final answer, 4 cos cubed minus 3 cos. Tan, well, tan is, of course, sine on cos. When I substitute in, to do tan, it is easier to substitute in the original result, where it's still mixed sine and cos. Because remember, tan is a combination of sine and cos. And then all I have to do is divide everything by the highest power of cos, and it will drop out nicely. Because the cos squared will cancel with the cos cubed, leaving me with sine on cos. Over here, I'll get sine cubed on cos cubed. The next one, cos cubed on cos cubed. Here, the cos will cancel with the cos cubed, leaving me with sine squared on cos squared. So everything then can be turned into a tan. And so I end up with 3 tan theta minus tan cubed theta on 1 minus 3 tan squared theta. So I get the trick, if you want of a better word, is when you substitute into these ones, leave it in the mixture of sine and coses. That's going to make the working out easier for that. Okay. They've asked us to show that x equals pi on 9 is a solution to this particular equation. Now, it is actually related to the last question we did, because we just came up with a relationship. Over there, you see we've got in the equation 8x cubed minus 6x minus 1 equals 0. What we just did, where is it? Down here, I've got cos 3 theta is 4 cos cubed minus 3 cos. Look at the coefficient, look at the power. Look at the coefficient, look at the power. It was 4 cos cubed, I've got 8x cubed. It was minus 3 cos, I've got minus 6 cos. So I could rewrite that as 2 lots of 4x cubed minus 3x and make a substitution, x equals cos theta. And then by substituting in, I can then say, what's inside the parentheses? Well, hang on, that's what we just shown was cos 3 theta. And we get a very simple little trig equation to solve. Now, why would I think of doing that? Well, the trick, I guess, is knowing the answer. Show that x equals cos pi on 9. So it's the cos result I'm looking for. So I want to play with the cos result. So I need 3 solutions because it's a cubic. So you just pick 3 consecutive solutions to cos 3 theta is equal to a half. Logically, pick the smallest ones we can. So I've gone, obviously, the first one, pi on 3 in the first quadrant, then 5 pi on 3 would be the fourth quadrant answer, and then I'd have to go back into the first quadrant again. 7 pi on 3 would be the third answer. Divide by 3 to get an answer for theta. We have pi on 9, 5 pi on 9, and 7 pi on 9. So yes, cos pi on 9 would be one of those solutions. Remember, that's the answer for theta. We want an answer for x, and we said somewhere, there it is, x is cos theta. So the three solutions to that equation is cos pi on 9, cos 5 pi on 9, cos 7 pi on 9. Another way you could do that, I suppose, because it is a show that question, you could substitute in cos pi on 9 and work that one out if you happen to know the exact value of cos pi on 9. Yes, you could use that backwards. Yeah, that's true. Okay. Now, let's work out cos pi on 9, cos 2 pi on 9, cos 5 pi on 9. So what we're now basically doing is playing with the roots of the equation. So it sort of now gets into a mixture of what we looked at back in polynomials. We know the solutions to that last equation was pi on 9, cos pi on 9 I should say. What was the next one? Cos 5 pi on 9 and cos 7 pi on 9. They are the three roots of the equation. So alpha, beta, gamma, it seems logical to multiply them together because our answer there has cos times cos times cos, would be 1/8. Problem is it's not quite what they've asked for. I've got the cos pi on 9, I've got the cos 5 pi on 9, I've got 7 pi on 9, they want 2 pi on 9. But remember, 7 pi on 9 is the same as minus cos 2 pi on 9. 7 pi on 9, we're in the second quadrant. In the second quadrant, cos is negative, and the acute angle would be 2 pi on 9. So I can replace the cos 7 pi on 9 with minus cos 2 pi on 9, and I get our answer of negative 1/8 for those three multiplied together. Classic question. By the way, if they don't ask you to find these results, then it's okay to quote these results. They can come in handy in some questions. So z to the power of n plus 1 on z to the power of n, and also z to the power of n minus 1 on z to the power of n. Okay, well z to the power of n we know is cos n theta plus I sine n theta. Z to the power of minus n, because that effectively is what 1 on z to the power of n is. So I can use the Moivres again, but now the power is minus n, becomes cos minus n theta plus I sine minus n theta. But let's use what we know about odd and even functions. Cos is an even function. So we know function negative x is the same as function x. Sine is an odd function. So function negative x would be the same as negative of function x. So I could rewrite that as cos n theta minus I sine n theta. So that was using our properties of odd and even functions. So now, if I add them together, the imaginary parts are going to cancel because now they're basically conjugates of each other. And so I'll get 2 cos n theta. And the subtraction one, it's now the real parts that will cancel. And I'm left with 2I sine n theta. So as I say, handy relationships to remember if they don't ask us to show it. But as you can see, it's very quick to show. Just use the Moivres. Comes out quite nicely. But if they don't ask us to show it, it's certainly fine to just quote it. And where can we use it? Something like this. Now I'm going to find an expression for cos cubed in terms of cos multiples of theta. Right? So before we had a formula for a cos multiple of theta in terms of cos thetas. Now it's sort of like the other way around. Well, it's cos cubed I want. No surprises I'm going to use this relationship. That's the whole point of the example. So I'll start with 2 cos n theta. But in this case, it's 1 theta, because I just want 1. And I'm going to say that's to the power of 3. And that will create my cos cubed theta that I want. But on the right-hand side, I'm going to say, well, hang on, 2 cos theta is the same as z plus 1 on z. And I'll expand the right-hand side out. So 2 cubes 8, z plus 1 on z, z cubed. 3 lots of z, 3 on z, and 1 on z cubed. Now if we group these together, we can use our little pattern again. So let me just regroup those. If I group z cubed with the 1 on z cubed, and I'll group the z with the 1 on z. The z cubed plus 1 on z cubed will become 2 cos 3 theta. The z plus 1 on z will become 2 cos theta. So I now know 8 cos cubed theta is 2 cos 3 theta plus 6, because we had 3 lots of the z plus 1 on z. 6 lots of cos theta. Divide both sides by 8, and we now have a relationship for cos cubed in terms of cos multiples of theta.